So I felt, to me, you know, the whole subject is walking on water, sort of. And for me, I mean, I'm walking on water, not the subject. And what the, is that not the right idiom?
No, it's great.
No, I meant to say I'm shaky. I'm
Walking
shaky.
on
Okay, but so you gave an amazing introduction to Entropy in the sense that I can see where all the what's hidden under the rug. But then somehow the beginning of when moving to the introduction of formula and the Hilbert space and the boundary theory. There, it sort of came as an axiom that it's there, and I wanted to understand what's sort of the starting point. What is it that you're requiring both from the field theory that you're putting there, as well as from the correspondence, so that we know that it works?
Yeah. Okay. So that's a good question. I swept it under the rug on purpose because it was using techniques that I didn't want to get into in this lecture, but in order to derive a formula like this, basically what you need is, where it comes from, is you think of the bulk theory as a quantum gravity theory, right? Or at least that's what we're thinking. And you have to make the assumption that to do calculations in this quantum gravity theory, you can calculate the expectation values of observables and partition functions using a path integral. And so a natural way to prepare states, like the ground state, thermal states in a physical theory, is using the Euclidean path integral. I guess, where's Anthony? Yeah, yeah, he told us how to prepare thermal states, a very similar idea. And in the case of the gravity theory, we imagine that there are some microscopic degrees of freedom, right? Or we think there are microscopic degrees of freedom. But a way that people have thought about doing quantum gravity, going back to Hawking in the 70s, is saying, let's do the path integral over the possible geometries. Right? So those are not actually the microscopic degrees of freedom. Like the geometries are macroscopic things. But if you think of the gravity theory as being some kind of semi-classical object, then one would hope that this would be a reasonable way to do the semi-classical gravity theory. And so there's a prescription which goes back a long way to doing these sum over geometry path integrals, for Euclidean path integrals to prepare states, and then real-time integrals to do time evolution. And if you take that prescription to be valid, all right, you can calculate partition functions, which are things like trace row. You can take trace row squared and trace row to the n, so you can get entropy-like functions. And you take the limit n goes to 1, appropriately, and you get the von Neumann entropy. And so you can look inside the guts of this path integral, and that's a lot of what actually happened, over the past 10 years. Like people really thinking, not just in the case of anti-de Sitter, but even in asymptotically flat space, what does the path integral look like? And seeing that you could extract this formula that looks like Ryu-Takeyanagi for the entropy. And so there's a lot of work there, which I'm not an expert on really how you do that kind of stuff, but it's justified. Those calculations are believed with the same level of belief that basically you can trust the semi-classical sum over geometries path integral. Basically, what is this minimum? It's a saddle point calculation in some path integral somewhere.
But do you expect this formula to hold for any? If you start from some space like the entropy space, you look at the field theory on the boundary, and you expect that whenever there is a correspondence which satisfies something, maybe there's a longer.
Yeah, even outside of ADS. Yeah. Yes.
Would satisfy.
Yeah, a formula that looks a lot like this. I mean, this is a simplified version, because It's not covariant. Like I've chosen a specific time slice and so on. If we get there towards the end of the talk, I'll write down what the covariant general formula is. But yes. Frank?
Can you give a little bit more intuition why this makes sense to take this integral over the possible geometry? Because that's the part I really don't have any. It's like the Hilbert Einstein action, I guess, is related to this.
Yeah. So why that makes sense? Maybe we can take that offline. I think that's something I want to think through a little bit myself. Like, I think we could come up with analogies where you have a semi-classical theory, and some sector of the theory is behaving, is basically obeying the classical equations of motion, and then I think actually that's basically is that the whole thing? Yeah, but let's take that discussion a little bit offline. Yeah. Okay, so I do want to get into black holes a little bit. And in this correspondence, so empty ADS was the ground state of the boundary theory. If you talk about a thermal state of the boundary theory, then you get a black hole. And one of these mixed states, the thermal state is a mixed state, so it's natural to purify it, and you can purify it in the energy eigenbasis. You get a sum over energy eigenstates. You take the square root of the weights. Oops, not H. The energies. And there's a purification. And people like to call this the thermofield double. In quantum information, we might call this the canonical purification. But it's just natural purification of the thermal state. And we could ask, what does this look like? So the geometry associated to this state at time equals 0 looks something like this. And so here's the CFT, right, which is a ring. And I purified. So I have a left CFT and a right CFT. So there's another circle on this side. And there's actually space connecting those two boundaries, right? And its topology is the topology of a cylinder. And so this thing is actually a wormhole, right? That's what the geometry of the purification ends up looking like. And
why is there space connecting the two?
So why is there space connecting the two? So there's a story about how you extract the metric from the boundary observables. And one of the boundary observables in the conformal field theory is something called the stress tensor. And so there's a prescription for how you extract the metric from the conformal field theory, from the field theory state. And so
of the connecting space.
I mean, in general, right? But in this specific case, it gives you this geometry. I gotta say one couple little things about this. So the energy eigenstates, this is a thermal state. So if you have a thermal state of some very large, huge number of degrees of freedom, if you choose a random energy eigenstate, its expectation values are going to be pretty much the same as they are for the thermal state, right? And so any one of these energy eigenstates looks pretty much the same for observables that we would measure on one side.
Can you help us? What's left and right? I don't think you even told us.
What is left?
L and R stand for?
Well, right is there was a CFT, a ring of qubits, right? And we purified it. I guess it was left here, the energy eigenstates. We purified that CFT with another copy of itself, right? So for every energy eigenstate, we wrote down another energy eigenstate in the second CFT. So that it means that if we trace over right, in this thermal field double state, we get the thermal state on the left, right? So they're just two mirror copies of each other.
And why do you call the thermal state a black hole?
Why do we? I'll get there, right? Right now it's a wormhole. Is all we know about it.
So sorry, but so far you just have the ring on of qubits, and then you verified it, so you got these two.
Yep.
And so far we have the right to think of the boundary as just those two.
The boundary is two rings now.
Yeah.
And I just turn them on their sides so I can draw the picture like this.
And now you're showing us the but now you're showing us where this wormhole came, the boundary part of the wormhole came from or something.
So what I'm showing you, let me. So this is boundary one,
Yeah.
boundary two, and then there's a single bulk, and the single bulk is connected.
Patrick, couldn't we derive that the two boundaries are connected, like using some entropy calculations plus the Ryu-Takanagi formula?
That's not how it was originally derived, but we could. Yeah, we will.
Okay.
But yeah.
Like these Greek lines connecting these two boundaries, are they part of the boundary as well, or they're part of the bulk?
Say again.
Like there are two lines, two green lines, and like that are more or less horizontal, right?
Yeah.
Are they part of the boundary or the bulk?
They're the bulk.
Okay.
Yeah, sorry. So the boundary, the left boundary is this ring.
Okay.
The right boundary is this ring, and then everything inside is just bulk. So one thing to observe, though, is that if I just take one of the energy eigenstates, say of the left, right? That's a state of the left CFT, right? So it's going to have some bulk, right? The expectation values of any observable that I'm likely to measure on the left CFT are going to be the same as they would be in the thermal state. So in particular, this region of the bulk should exist for one of those, for a typical one of those energy eigenstates. But somehow it's not going to be connected to the right. And so this is an example where if I take a bunch of disconnected geometries, right? If I have an energy eigenstate on the left, energy eigenstate on the right, if I look at their product state, that's going to be a pair of disconnected geometries. But I take a big enough superposition of them, and they represent a spatial, a connected geometry. So this is a situation in which entanglement is leading to the creation of space. Right? So Lenny likes to say ER equals EPR, Einstein-Rosen bridges, wormholes are equal to Bell states. I don't know if that's supposed to be an analogy or a metaphor, but this is a situation in which it actually happens.
But how do you see that they're connected? I mean,
How do we see that they're connected? Okay, so again, I can't do that calculation, but in the CFT, again, there's a prescription kind of coming from the story that I was telling you before about how you extract the metric in the bulk from the stress tensor in the boundary. And so you just turn that crank and you find the metric. Or, as Scott was saying, if you follow the prescription that I just told you about where entropies come from, right? We can start calculating entropies to figure out whether the bulk is connected or not. Because we know that the bulk is related to geodesics, or the entropies are related to geodesics in the bulk. Okay, so.
Can I ask one more question?
Yeah.
So how should I think of this picture now? Should I think of it as a nice trick that you did? Like, is the wormhole real? Or is it just something that you are now, using to represent?
This is a matter of taste.
Black hole.
Okay, so this is a little bit of a matter of taste, right? If you want to take if you don't want to have your worldview shaken too much, then you just take the point of view that all we want to do is find ways of doing calculations in conformal field theories. And we find there's an effective description involving gravity, the stress tensor gets mapped to the metric, et cetera, blah, 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 right? And you just say, okay, well, in my effective theory, there's a wormhole. and then you can go home and you sleep at night, and there's nothing to worry about. But this could have implications for the way that you think about the structure of our world.
In the first part, your bulk had a very nice coordinate system. So
Oh yeah, you want to see coordinates?
is there a coordinate system
Yeah,
here?
sure.
Okay.
Let's lay down some coordinates. So the entanglement wedge is. I did want to talk about the entropy. So let's calculate the entropy of the entire right CFT. Okay. So I want to take my region A is this whole circle. And remember the homology condition says that I should think about bulk regions I should think about curves, gamma. When I take the union of the boundary and gamma, I get a bulk region, okay? And so this squiggly gamma would be allowed, and also this one around the waist of the wormhole is allowed. And the way I've drawn it, you can kind of, it's meant to be suggestive. I drew the curve around the narrowest part of the wormhole, and that will actually give me the entropy, the length of that curve. And so the entropy of the CFT is 1/4 Newton's constant, the length of gamma. And this is Hawking's formula, right, for the entropy of a black hole. The entropy is supposed to be the area of the horizon. This waist, it turns out, is the horizon. So this Ryuta-Kinagi formula generalizes Hawking's formula.
So we could say that the two boundaries must be connected, because if they weren't connected, then the entropy of each boundary would be 0.
Yes. Yeah, if you like.
It would be an entangled state.
Yeah. Although that logic suggests that any purification of the right CFT will give me a connected geometry, and that's probably overstating the case, right? Lenny might say such a thing, but I think there are a lot of additional conditions on the state before you can interpret it as a wormhole.
But isn't what Scott said just the truth? Isn't that what Scott said just the truth? I mean, if you do get a non-zero entropy, then they must be.
If you define a wormhole as entanglement, then yes.
Or you could say maybe it's only valid if we start with a globally pure state. If we don't in physical reality have a pure state, then we're not allowed to do this.
Well, so here's another a counter argument, right? Take this state that we just talked about, this thermal field double, and then apply a Haar random unitary transformation on the left, right? So now you've completely messed up the geometry, the degrees of freedom are all mixed together. I would not expect there to be any kind of smooth geometry interpolating from the right to the left in that case. And it takes a radical redefinition of what you mean by a wormhole. And actually, I was going to call on you at this point, right? So there was this controversial experiment a little while ago, in which people asserted that they made a wormhole in the lab, right? And Scott had a good quote in the New York Times. What did you say exactly?
I said, if we're going to say that this brought a wormhole into actual physical reality because they simulated it on a 9-qubit quantum computer, then why not say that I bring one into reality when I just draw like 2 curved lines on a piece of paper?
Right. So I'll interpret what you said
All
as a version of what I was suggesting. The entanglement is necessary for the geometry, but it's not sufficient. Okay. So there was a question. Coordinates.
What's your blank in the red box?
Oh. The entanglement wedge is the horizon. Oops.
Why is this a black hole? Why is the thermal state a black hole?
Okay, so.
I mean, why is
So,
this connected to?
Right. Well, remember I was just telling you, you can infer the metric from the stress tensor. So the metric is the bulk quantity. The stress tensor is going to be the boundary conformal field theory quantity. And the metric you infer, if you just throw in the thermal state, is this one. And this metric, which might not mean much to you, but you can see there's a time, the time portion and a spatial portion, radial and angular. right? Because it's 2 plus 1 dimensional bulk. And there's a coordinate singularity at little r equals big R, right? And it's not a real singularity in the space-time, but at this point, at little r equals big R, that is the horizon of the black hole.
So can you explain these, what's little r, what's little r?
What's happening? Oh, so when little r equals big R,
Label, no, I'm missing the labels on the diagram. What's
the labels of what T and R file.
Yeah, okay.
Oh, sorry. Yeah. So I don't have to tell you what the coordinate, I mean, you can sort of, there's no time in this picture.
Yeah.
It's just space. And the, let's see, the radial coordinate, it takes you around the CFT. And the angular, the angular coordinate takes you around the CFT. The radial coordinate kind of brings you inside. And this metric, if you analyze it, it does involve time. And it's basically the Schwarzschild black hole stuck inside ADS. Right? We don't have time to go into it, but that's what this thing is. And so you infer, as I was saying, from the boundary state that there's a black hole there. And I have a few comments about these parameters, right? The mass, there's little l. This is the radius of curvature of the ADS space, which I'd set to 1 before, but now I've included it. Newton's constant, the mass of the black hole. So the radius of the black hole grows as the mass grows, as you would expect. And the black hole has a temperature, which goes down with the mass. Okay. Or inverse temperature.
That would happen for any Gibbs state, for any thermal state, for any temperature?
Unless it corresponds to a black hole so tiny that it doesn't reach that it can't be at equilibrium with the radiation. Because there's this issue that we talked about, the black hole radiates, the radiation goes out to the boundary, it comes back, it gets reabsorbed, and so you. This does not describe an evaporating black hole. It describes a static black hole.
Wait, beta is the inverse temperature?
It is the inverse temperature.
But I thought that the temperature should be inverse with the radius. Right?
It's different in ADS. Yeah.
So the bigger you make the black hole, the hotter it gets?
Well, it's related to the, relative to the ADS scale. Yeah.
Oh.
Yeah. Okay, so I do want to present this picture though. So this metric here, it has this radial direction, r greater than 0. And so it really just describes one side of the picture, right? But you can take that metric and analytically extend it, right? That there's a bigger metric. And what you find is a black hole with 2 outsides, right? So you could fall into the black hole from the right and you could fall into the left, but you meet in the middle. And this is a picture that kind of describes the causal structure. That this is a particular set of coordinates that takes all of infinite space and squeezes it into a finite box here. And time goes up from left to right. So there's a time on the left. I have to remind my pen. There we go. That's connected. Right. So in this picture, this is a particular set of coordinates. Yeah.
Are the labels L and R related to the constants in the metric?
Are they related to
The constants L and R in the metric?
Oh, no. Sorry. L and R here just mean left and right. Yeah. So they're not constants. They're just
I think I still don't understand the coordinate system particularly well. Like what takes you from, what's the radial direction? Does it move you within one CFT or does it go from left to right?
It doesn't go all the way from left to right in that metric. The metric only covers a portion of the space-time. Basically, this upper right portion. in this picture, but I'll explain this diagram in a second, or right now. So this is, there's some set of coordinates, very curved, in which the black hole looks like this. And now time goes up from left to right, so the entire CFT is just a point. So at every point, there's, or rather so every bulk point, there's a full circle. And, right, the horizons of the black holes are these dotted lines. And in this set of coordinates, they're very nice because light rays travel at 45 degrees. Okay? And there's the singularity of the black hole is supposed to be up at the top. And so if you're in this region here, any signal that you can send out has to travel inside this this wedge from 45 degrees to the left to 45 degrees to the right. And so any signal that you send is going to hit the singularity. Right? So this is the interior of the black hole. This is the right outside. If you're on this side, if you just sit where you are, eventually you land inside. And likewise on the right, and two light rays from the left and the right can meet in the middle. Right? So this is this region here, which from the outside looks like a black hole. It is a kind of a wormhole from the left side to the right, a non-traversable wormhole, right? Because there's no way to start here and travel at the speed of light or slower and end up on the other side, right? If you start here, travel at the speed of light, you hit the singularity. You're not able to get out to the other side. And so this is what's called the Penrose diagram. It describes the causal structure of this two-sided black hole. And I wanted to, in these lectures, I wanted to show you how you could calculate things, okay? So I gave you a metric here, and then I asserted that you can find coordinates that cover both sides at the same time, right? The r and phi coordinates did not. But there are something called Kruskal coordinates, and they look a lot like this Penrose diagram. Again, light rays travel at 45 degrees. That's u equals 0. This is one horizon of the black hole, the other horizon, the interior region, the right exterior region. And except that the singularity occurs at u times v equals -1. And the boundary occurs at u times v equals 1. So the boundaries here are hyperbolas. And this hasn't squashed everything down into a finite box because the space-time extends out to infinity, in these UV directions. But it looks a lot the same. And I'm just going to flash this at you because we don't really have time to go through it. But here is the formula that relates the r, t, and phi coordinates to the u and v coordinates. Okay, and so if you're comfortable with the r and t coordinates, you can use this to calculate the metric, or you can look it up, and so on and so forth. Right. So this is the metric of this two-sided black hole, and it can be inferred directly from the CFT state. And what's nice about this particular, I also defined these T1, T2, X1, X2. This is some embedding of the three-dimensional geometry and a four-dimensional geometry. And it's nice because there's a very simple formula for the geodesic distance in terms of these X's and T's. So there's the formula for the distance between any 2 points in the wormhole geometry. Okay. So can't really imagine it being much simpler than this. Reasonably simple. And again, we can stop and think, how would you prove this? Euler-Lagrange equations, right? That's how you do this. Okay, so what do we find here? If we just take this formula for the geodesic distance, we could ask, what is the distance from the left, from a point on the left to a point on the right, at the same angle, at the same angular, at the same time, well, at the same angle phi. And you work out that there's this formula here. And let's just say that we're going to talk about the same times on the left and the right. So t is t left and t right. Probably right there. We want to take this formula. We want to know what the distance is. We have the log of the hyperbolic cosine. Again, if the argument of the hyperbolic cosine is big, it's just the exponential. So the log of the hyperbolic cosine is just nothing, or it's just a null operation. And so we just have the radius times twice the time over twice the radius of curvature. So we have radius of the black hole times the square of the radius of curvature. And so what we see here is that this black hole, or the wormhole, from the outside, the black hole just sits there doing nothing. But the inside of the black hole is changing as a function of time. It's getting longer and longer and longer and longer. Its length is proportional to the time at which we asked we look. And so this geometry is not static. It's changing. And you had a question?
Yeah, again, in the basics, I don't understand. So you started from a black hole, which,
Yep.
Later you argued why it's related to, it's equivalent to the thermal state.
Mhm.
And then you purified it as, I mean, to me,
A
it
formal
seems like,
operation.
to me, it seems like an abstract, I mean, just a mathematical operation.
Mhm.
But then you're treating this purification as a mathematical, as a physical thing, as if it exists there. I guess assuming, or is this under the assumption that this thermal state comes from a truly pure state in physics, or where does this purification come
Right,
from?
so the reasoning goes that if I purify the thermal state as a state of another CFT in the way that I did, then I can still use the ADS CFT correspondence to go from the metric of this. The new CFT consists of 2 rings instead of 1. I just think it can be like superimposed right on top of each other. Instead of a qubit, it's instead of d, it's now d squared, right? So it's a new CFT, but I can use the same rules to infer the bulk metric. So I use those rules, and this is what I find.
Okay, but you do treat the two boundaries as if they do exist.
Yeah, I mean, let's just take the pedestrian. We're doing conformal field theory, and we want the effective description, right? And so we just turn the crank. We say we have a conformal field theory that has two subsystems that I'm calling left and right, but together there's one stress tensor, and I go from the stress tensor to the metric, and the metric is this one. So it's this much has been around for 30 years, or close to, yeah. Mm-hmm.
So this is a consequence of having just one. It's not a mix.
Yeah, you have to treat it as a single
So we're
object.
not having some kind of like consequence.
You're not stitching things together, no.
So does this imply that the entropy of the black hole is increasing?
Yeah, so we can use this to calculate the entropy. Yes. Well, let's okay. Thank you for the segue. Let's calculate the entropy. So the entropy of the black hole, we worked out up here, the area of the entropy of the black hole. If we look at this metric, which covers the right-hand side, there's no dependence on time, right? I mean, if you have there's dt, but there's no dependence on t, right? There's a dependence on my radial position here, but there's no dependence on t. And so this tells me that anything I can measure only on the right is going to be, it's not going to change with time. That the black hole looks like it's static from any one side. So the only thing that's changing is inside. Okay, so let's calculate the entropy. And in particular, sorry, the black hole entropy stays the same. But things do change. And so the kind of thing that we can ask about is, let's take a region A, which is half of the left boundary, a region B, which is half of the right boundary, and try to evaluate the joint entropy, S of AB. So now we're going to have to apply that homology condition again. Can anyone give me a candidate? Yeah. So what do some candidate bulk gammas, bulk curves that could be used to calculate the entropy look like? right? So they have to satisfy the condition that A union B union my bulk curves are the boundary of a bulk region. Okay, so Dorit has proposed oops, she did not propose that. She proposed this. So there's an example, right? The yellow region, the boundary of the yellow region is A, B, union gamma 1, union gamma 2. So that's perfectly good. And what's another option? Yeah, okay. There's another option. And so the first configuration, do you think it's going to dominate for early times or late times? Late? Early, right. So we learned that the wormhole is getting longer and longer as time increases. And so gamma 1 and gamma 2 are getting longer and longer and longer as time increases. So at some point, well, I should say gamma 3 and gamma 4, they never enter the black hole. And so the lengths of gamma 3 and gamma 4 never change. So eventually, gamma 1 plus gamma 2 is larger than gamma 3 plus gamma 4. So the first configuration dominates for early times, and the second configuration dominates for late times.
Again, how is the thermal field double state evolving that reflects this?
Phases.
Okay, just
That's
phases.
it. All of quantum mechanics is only phases.
Yeah, fine. Fine.
Yeah.
Okay.
Yeah. And so what does this mean? Well, if we think about the mutual information of A with B, that's entropy of A plus entropy of B minus the joint entropy. Once we reach saturation, what happens? We have this configuration, right? And the joint entropy is the entropy of A plus the entropy of B. So the mutual information is 0 for late times and greater than 0 during the growth phase. And so that's what happens with a black hole.
Sorry, Patrick,
Yeah.
once the wormhole is so long that we never want geodesics to straddle the wormhole, then how can we continue to use entropy to calculate what's going on or tell us that it's going to continue to get longer?
Maybe we can't actually. So there are other quantities that are calculated by geodesics, certain kinds of correlation functions, and you'll see the correlation functions, they decay exponentially with the length of the geodesic. So those things will continue to change. But I think you're right actually. In this case, it saturates at a given time.
Right.
Yeah,
Okay.
you stop learning anything.
Thanks.
All right.
Don't you already see here time irreversibility?
We don't see time irreversibility.
The prediction would have to be that when the phases all line up again like they were before, then the wormhole has to shrink.
Oh, sure. Yeah. Okay. So there's an issue, yes, which I swept under the rug, which is that if there are a finite number of degrees of freedom effectively in the conformal field theory, eventually we get recurrences at some enormous times in the future. And so there's some time after which the GR description no longer ceases to be valid. And it's not very well understood how long that is. But it has to break down eventually for exactly that reason. Okay, so there's been no complexity so far in this discussion, but it's time to introduce a little bit of complexity. And this is Susskind's puzzle. Okay, so we have this two-sided black hole, which is really a wormhole, and we've learned that the length of the wormhole grows linearly as a function of time, at least for exponential times, and then something strange might happen. And as we were just discussing, the entropy, or the joint entropy, the mutual information, this saturates early, right, in linear time. I'll just say in polynomial time. And so he just asked the question, what is the boundary holographic dual of the bulk wormhole length? Exactly what Scott was asking. Because he wants some let's call it measurable, provisionally, some quantity in the bulk that correspond, or in the boundary that corresponds to bulk wormhole length. Bulk wormhole length is a pretty straightforward observable in the gravitational theory, right? It's one of the simplest things you can write down. The shortest, length of the shortest path between 2 points. And so a general rule in this ADS-CFT game is that natural quantities on one side have some natural description on the other side. And so he wants to know, what is the boundary holographic dual of bulk wormhole length? And back in 2014, he was thinking about this, and he said, okay, he needs a quantity that will grow linearly with time for time exponential in the number of qubits, the number of degrees of freedom. And he scratched his head looking for a quantity that would have that property. And what he came up with was computational complexity. Of the CFT state. So relative to this thermofield double, if you start at the thermofield double, you can ask how many additional gates are required to convert that state into the state at some later time. And he said that should be the boundary dual of wormhole length. So let's just check that makes sense. Is it a CFT property, right? There's a Hamiltonian in the CFT. We can trotterize it or use some fancier method of Hamiltonian simulation. And if we use an optimal method of Hamiltonian simulation, the number of gates will be proportional to the amount of time that we have to simulate for. We're like, well, okay, it checks out in that very limited sense. But when Lenny proposed this to me back in 2000, or he suggested, I thought he was crazy. He suggested a lot of bold things in his lifetime, but this one just seemed completely unfounded, right? Like, what kind? You want something that's is proportional to time. You say, what could possibly be proportional time? Computational complexity. And that was basically the argument at that point. Okay. Okay, so I said a bunch of this stuff already, right? So if we say that the state at time t, I'll call it psi of t, we get it by evolving from the thermofield double state for an amount of time t. There's a Hamiltonian on the left, a Hamiltonian on the right. You do a Hamiltonian simulation on this thing, Hamiltonian simulation on that thing. The number of gates is going to scale proportionally to the time. And if there's no shortcut to that Hamiltonian simulation, and these Hamiltonians are chaotic, right? And chaotic in some very strong sense. And so there's no reason to think that there is a shortcut. But if there is no shortcut, then this statement is true. And it was later revised, for reasons we could get into not the wormhole length, but the wormhole volume properly defined, being proportional to the circuit complexity. But again, what flimsy evidence? Like, why would anyone believe such a thing? Well, after he proposed this, he and Douglas Stanford, building on work that Douglas Stanford done with Steve Schenker on shockwaves, found that there is more evidence. So this is going to be the story of shockwaves with these black holes. And I think I'll end after this. But imagine sending a few photons at energy the same order as the temperature. So you're not sending in very hot photons, very energetic photons. You're sending in photons that might be like 10 times the temperature or something, right? 5 times. And then you ask, and you're sending them into the black hole. They'll be absorbed by the black hole. The black hole will grow by a little bit. But if the energy of these photons is small compared to the mass of the black hole, you wouldn't expect much to happen, right? So the picture is something like this. At some time in the past, TW, you send in some photons. They enter the black hole. The black hole absorbs a little bit of extra energy. Black hole grows a little bit. No biggie. But it turns out that there is a very large blue shift because of the curvature and the geometry. And in the frame, which is relevant to talking about the interior of the black hole, right, these Kruskal coordinates, you find that there's a massive blue shift, right, growing exponentially with how long in the past you sent in these photons. And so the exterior geometry is barely affected, but the interior geometry is strongly affected. And again, I just want to sketch to you how you do these kinds of calculations. So here's that Kruskal picture. There were some coordinates that I spoke about. At some time in the past TW, you send in this, you send in this little energy pulse. It enters the black hole, right? But when it enters the black hole, you should think of it as being incredibly energetic, okay? And it's a shock wave. And so what you end up having to do mathematically to deal with this situation, on one side of the shock wave, you have the Kruskal coordinates. On the other side, you also have Kruskal coordinates. But they describe different black holes. Actually, you don't have to really talk about the shock wave too much. On the left-hand side, where we drop the pulse, the black hole is now mass m plus e. On the right-hand side, the black hole is seen as having mass m. So you have to glue these two solutions together. And so when you glue geometries, you can ask, well, what do I need to do when I glue geometries? Remember, there's a circle, an angular direction, which is suppressed in this picture. So the radius of the circle should be the same as you cross that gluing. And then you also want time to flow continuously, the proper time experienced by an observer who crosses that cut to increase continuously. So you just use those two gluing conditions, and you get a new metric, okay? And the new metric, it really does just look like two glued Kruskal wormholes, but with a shift, right? So here is the past horizon of one, and it doesn't match up with the past horizon of the other. So there's a, it just looks like it looks like the geometry on the left, but someone who crosses the shock wave gets bumped discontinuously to another location, to a different coordinate. And so I just want to sketch that out. Like this is something that it's described in the Schenker Stanford paper in detail, and you can follow it if you like. But once you've done that, again, we care about geodesics, right? And I gave you a formula for the length of geodesics in this wormhole geometry. But now there's this kink. So if I have two boundary points, like a boundary point here and a boundary point there, if I want to calculate the geodesic distance, I have to optimize over the points at which they hit the kink, right? So there's a one parameter family of geodesics that I have to optimize over, and I find the minimal length, right? And here's the answer. There is the length of the new wormhole. And what is there to say about this? The difference shrinks exponentially with time. So let's just think about the time t equals 0. And so the distance has this extra piece, alpha, right? And what does alpha look like? Energy over mass, exponential in the time that we dropped in the perturbation. And so an exercise for you, because Dorit wanted exercises, set time equal to 0 and express the wormhole growth, the log of alpha, in terms of the time at which we dropped in the perturbation, the entropy, the energy, and the inverse temperature. And I wrote down formulas for all those things. And what you get as your answer is that the volume or the length goes as the time in the past at which you dropped in the perturbation minus twice this quantity t star. So the volume doesn't start growing until there's sort of a delay before the volume starts growing, right? And t star is this quantity known as the scrambling time, inverse temperature times the log of the entropy. So this came up, for example, in my paper with John Preskill about black holes. It's a very important quantity. It gives us the time scale for information to become fully delocalized in the black hole, or in the boundary theory. And so this is some formula, and it's now more interesting It's a more interesting formula than just saying that volume grows with time proportionally, right? It's saying that the volume, it was growing with time, but if we fix the time and then we think about dropping in a perturbation, there's a very specific form describing how the volume should change. And we could compare this against the computational complexity hypothesis, right? Because T star, right, involves a log of the entropy. Yeah, it's something non-trivial.
Wait, I mean, couldn't that formula predict that the volume should be negative?
So let's say the growth is 0, or this is only for TW significantly larger than T star. Yeah. Okay. Because I was neglecting this, yeah. I think I was neglecting, well, yeah. All right. Yeah. Okay.
So why is this another?
It's not a check yet, right? It's a prediction. Because we're saying, okay, Lenny predicted, or conjectured, that wormhole volume should be proportional to complexity. And he verified it in a trivial case, right, where wormhole volume is growing linearly with time. Here's a non-trivial case.
In what sense does it verify it? I mean, what's the correspondence?
Okay, well, here's a case where the wormhole volume is non-trivial. And now we have to do the work of trying to estimate the size of a circuit that will actually make that state. So let's think about how we would make that state. We're interested in the state at time t equals 0 that corresponds to having dropped in a perturbation at time tw in the past, right? So how do we do that? We start with a thermofield double state. We evolve it backwards in time. So this is on the left-hand side. We evolve it backwards in time, tw. So now we have the state on this time slice. We apply the perturbation, which I'm calling w. And then we evolve forward in time. Like that, okay? And then we get a state again at t equals 0, which corresponds to what the state is going to be at that point. And so this state here, I'll draw it as a circuit. We start in the thermofield double. We apply the backwards time evolution. We apply the perturbation. We apply the forwards time evolution. And if we just looked at this, what we would predict would be that the computational complexity would be proportional to twice TW, right? Because it'd be this portion, which is proportional to TW, this portion, which is proportional to TW. Now, can anyone look at this and suggest a way to do it better with fewer gates? Cancels, right? Right. So the right-hand purple gates are just the inverse of the left-hand purple gates, and so we can just cancel all of this with all of this, and we can cancel all of this with all of this. Right? Yeah.
Computational complexity, the depth of the quantum circuit, the total number of gates in this one.
I mean the size, I think. Yeah.
So then it's not proportional to t, right? If you evolve the Hamiltonian for time t, it's more like n times t.
That's true, depending if I'm keeping track. So maybe I should talk about the depth.
Well, wait a minute. I mean, as long as you assume that TW is large compared to T star, then these like light cones, like you'll get a little bit and then they'll stop. Isn't that what you want?
Yes, exactly.
Okay. Yeah. All right. So this picture is a little.
This picture is a bit misleading.
Yeah.
So let's let's fix that. So we have cancellation outside the light cone, and in the actual model, the circuit is not geometrically local, and so the light cone grows exponentially with the depth, right? So I partially erased this. Exponentially, something like that, with depth. And so we saturate in an amount of time which scales like the logarithm of the number of qubits. And n is basically the entropy, right? The number of qubits is the entropy of the system. And so the computational complexity, the relative complexity of converting the thermal field double state into this perturbed state is no more than TW minus twice the scrambling time or the saturation time.
Sorry, why don't you get twice TW? Because you have the.
Well, you're canceling on both sides.
Yeah, but we just said that the cancellation only goes for this limited amount, and then it stops. I mean, because
Right. So
of
the two I think is coming from the fact that there was cancellation here, and then cancellation here.
Right, but I'm asking why isn't there a 2 in front of the TW? Because we have to apply all the gates and
Oh, I see.
And then all the gates going forward.
Okay. Actually, maybe that's right. So the thing is, yeah, we have to be a little bit careful. Also, with the definition of T star is not really well defined beyond that constant, or at least the correspondence between the scrambling time and the spreading time. Yeah, there's a hidden constant there, right? Because we want not just for the information to spread, but we want the information. We basically want some 2 design type condition, right? Like we want the information to generate quantum error correcting codes, or we want the spreading to generate error correcting codes. So anyways, I think there's a little bit of,
Okay.
well, I think there's a little bit of wiggle room on this constant. Lenny might have a better argument for why it should be exactly 2.
Okay, yeah, but I still want to know why there's a 1 in front of T sub W.
Well, because yeah.
Yeah.
Yeah, I mean, the only thing that's meaningful here is the ratio,
Fine.
and I don't think that's
Fine.
off the top of my head. I don't know that that's extremely well defined, but I'm gonna provisionally say that Lenny might have an argument for why it really should be exactly 2. So, anyways, now we do have some agreement though, right? The important thing is that you have this TW minus some quantity which is logarithmic in the number of degrees of freedom, right? And I think that's a non-trivial agreement. It's not a proof by any stretch, but it's an indication that it's not completely ridiculous to have made this conjecture. And I should probably let you go for lunch. There were all kinds of other things I was going to tell you about, in particular black hole evaporation. You can let the arbiters decide there. But yeah. Okay. So one thing that oh wait, what's your? I think I had something here. Yeah, there's a big punchline that I won't have time to get to. Oh wait, no, I think we should let people have some lunch.
The big punchline?
Okay, well, the big punchline. Okay, so let me just show you the big punchline, but I won't have time to really explain it. All of this was done in the context of anti-de Sitter space, right, and this EDS-CFT correspondence. But it turns out that a careful inspection, I think we were discussing this, of the formula for black hole for the entanglement entropy, it can be applied in asymptotically flat space. And so you can apply it, and this is what Jeff Pennington and others did in 2019, to an evaporating black hole. And you can try to calculate the entropy of the radiation as a function of time. And this is a thing that Hawking couldn't do, right? Or it's one of the things that he couldn't do, or he didn't seem to be getting the right answer. And when you do when you look at an evaporating black hole and you calculate the entropy of the radiation as a function of time, it does exactly what you would expect a lump of coal to do. Okay, if the coal started off in a pure state, it starts radiating, so it becomes entangled with its radiation. But as it burns itself off, it shrinks, and eventually there's nothing left. And so the entropy of the lump of coal goes up and then goes down again. And a black hole does the same thing. That's not very exciting, except that we can do the calculation. We actually know what's going on. But the much more interesting thing is that you can apply entanglement wedge reconstruction to this situation. So you can ask, if I'm interested in the the entropy of the radiation, where's the extremal surface that I use to calculate it? And the extremal surface, you end up having to use for old black holes, an extremal surface which is inside the black hole. And so there's an entanglement wedge sitting inside the black hole, which means that if you have an operator inside the black hole, you can reconstruct it in the radiation. So that's actually a huge punchline. Because what have I just told you? I've told you that this purple portion of the interior of the black hole is encoded in the radiation, right? What does it mean to be encoded in the radiation? It means that the quantum degrees of freedom of the interior are equally well in the exterior. So you would think, like our picture of the world is that there's space here and there's space there, and they're independent of each other. But in this picture, all of this, this entire region inside the black hole, it's accessible outside. It's there. There's no distinction between inside and outside. They're the same quantum mechanical degrees of freedom. Yeah. If I wanted Pauli operator X, measuring a qubit right here, there's a logical Pauli operator X in the radiation that will tell me the answer. And so, in the same sense, that position and momentum are complementary degrees of freedom in quantum mechanics. They're no longer independent of each other. The interior and the exterior of the black hole are no longer independent of each other. And this is something that was conjectured back in the 1990s, but now we can calculate it. We can verify it, right? This is, I won't call it a fact, but under the, we've been talking about this sum over geometry's path integral. Under the assumption that that path integral properly calculates quantities in quantum gravity, this is the answer. The interior and the exterior of the black hole are not independent. The interior degrees of freedom, at least some of them, when they correspond to the entanglement wedge of the radiation, are encoded in the radiation itself. So the radiation has inside it the interior. And you might wonder, why don't we see massive violations of causality, right? Because now there was this, that was the definition of a black hole. No information inside could get out again. It seems to be that the semi-classical causal structure predicted by general relativity is enforced at a practical level by the fact that decoding the radiation would be exponentially hard. That these are error-correcting codes. They're pretty random. They're generated by chaotic time evolutions. And so generically, the complexity of decoding, we expect it to be hard. And that seems to be how the causal structure is preserved.
Sorry, can you explain this? What do you mean? So violations of causality, understand. What does this mean? Is semi-classical causal structure?
Okay, so violations of causality, stuff inside the black hole should not get out, right? But stuff inside the black hole does get out. In fact, it's encoded in the radiation. So that is a violation, formally speaking, of causality. But you could ask, is it one that would ever affect an observable that that we could measure in a practical sense, right? And a condition that you would want to impose on the observable would be that you could implement a time polynomial in the size of the black hole, or the entropy of the black hole. And it seems that won't be possible. We don't know this. This is a conjecture, but that seems to be the nature of the sense in which the causal structure, the old causal structure preserved by general relativity, survives in this theory. Yeah, Frank.
If you have a violation of causality, it means that you would be able to send information from the inside to the outside?
Well, right. So no.
Because that's
right.
causality.
That's the point, because the information gets encoded non-locally all over the radio, or the information inside the black hole is encoded non-locally with these in the radiation, all over the radiation. The only way to access it is to collect an order 1 fraction of the radiation, do some extremely difficult exponential time quantum computation. And so...
But I thought that causality had to do with sending information.
Yes. Well, so the sending would be, you send from the inside to the union of the entire outside of the black hole. General relativity does not allow that, right? If you say there's no communication from the interior region to the entire exterior region, that is happening here. But from a practical perspective, there will be no communication from a location in the interior to a location in the exterior. It's going to be too delocalized and difficult to extract. And there's been papers, thinking about those questions. But I don't want to keep you for too long.
Patrick, can I just ask one thing?
Yeah.
So the entanglement by reconstruction to reconstruct this on the boundary theory, right?
Yes. So
And that's not the same as.
it's not the same thing. So there is potentially. Let me think. I'm going to put an asterisk on that because entanglement wedge reconstruction has been demonstrated to a level of rigor that I'm fairly confident, that I'm confident in ADS-CFT. I am not 100% sure that has all been done properly in asymptotically flat space. So if someone's looking for a project, I think that's actually a good thing to sit down and see whether the arguments all go through. I suspect they do, but if it hasn't been done, maybe that's something some of our group members should do.
So in asymptotically flat space, the entanglement wedge reconstruction would reconstruct where? Where's the error correcting codes?
So now instead of talking about a region of the boundary, you take a region of the bulk. Now there's only one theory, but it's you collect all the radiation, and there's an entropy formula that behaves the same way there, which I had here but I skipped over. Yeah. So you just have to make sure that the arguments that were made that didn't really depend much on ADS-CFT also work, because they were really entropy arguments at the end of the day. Now, my intention, I have Adam teed up here to talk about complexity. So there's a lot more interesting things to say about complexity and quantum gravity, but Adam has COVID, so he's not giving that talk. But right after lunch, Fermi is going to say something. I don't know exactly what about complexity and quantum gravity, so hopefully I've set things up for him. And maybe I'll end it there. And thank you for your inquisitiveness and your questions and for slowing me down. And I'm happy to take any questions, happy to go to lunch with anybody. That's it.
So when you say you verify these theories in some examples, this corresponds to some examples of the circuit complexity of some state. And you see upper bounds, like, are these also lower bounds, or is it just?
We don't know that they are lower bounds. So under the assumption that there's no shortcut, under the assumption that the only way to produce that state, which is the result of this chaotic time evolution of this Hamiltonian, is to actually simulate the Hamiltonian. But that's definitely not been proved. Or rather, it's true trivially subject to that assumption, but that assumption has not been demonstrated in any way, shape, or form.
Is it fair to say that basically like the question of reversibility of microscopic dynamics and classical mechanics and compared to the growth of entropy, which basically the resolution of that sort of semi-paradox is that you don't know. I mean, of course, great. Thermodynamics shows the entropy grows, but not microscopic. It's a little small. Is it sort of the same type of resolution that basically if you knew everything, then everything is reversible. But since you don't know, since everything is local, then you do see growth of entropy. Or is this too simplistic?
So I think you can you can certainly talk about some coarse-grained entropy of the black hole. The entropy of the black hole, or the coarse-grained entropy of the radiation, right, will just keep on going up, right? Like its thermodynamic entropy will just keep on increasing. Again, just like a lump of coal, right? Or if you're burning some coal, and you ask about the smoke and the radiation byproducts, the thermodynamic entropy is just going to increase proportional to the amount of stuff you collect over time. Even though at the end of the day you have a pure state. So the same is true of the radiation. I think, if that's what you're thinking. But the coarse-grained entropy, like if you just look locally at the radiation and you assign an entropy to it, and you assume there are no correlations, and you're just going to get a Hawking-like answer. And so that's true. And one thing that's interesting is that the story to get to the black hole, like say to calculate the entropy of the radiation, it involved this long series of ideas, like thinking about black hole complementarity, thought experiments, quantum error correction, this Ryu Takiyanagi formula, its generalization. Like there's this whole sequence, intellectual sequence. But at the end of the day, you set up the calculation to calculate an entropy, right? And you do a saddle point approximation using this sum over geometries, which is exactly the kind of thing Hawking was doing back in the 70s. And from this perspective, he sort of set up the calculation wrong, and he missed some saddles, right? So he just took what he thought was the dominant saddle and didn't realize there were these other ones. And so that's sort of formally, when you look at it, the one that he thought was the dominant one was the one that just had no correlations in it, that could actually make the entropy go back down. And so that, so he could look at the story now and not know anything about quantum error correction, but just look at the calculation like, oh yeah, okay, that's where I went wrong. I should have seen those saddles. I should have calculated entropy in a different way. Yeah.
Does the thermal field double state tell me anything about the Gibbs state?
Does it tell you anything about the Gibbs state?
Calculation, like if you just evolve the thermal field double state, you get this closure. So the Gibbs state is actually not changing.
Yeah, well, so I think it does tell you some things. Like, you're probably aware of this. Like the thermal field double, I think that Guy Vidal and friends had an algorithm for preparing mixed states of conformal field theories that was motivated by this connection to wormhole geometries. Like they do some identifications in the tensor network because these black hole geometries are actually quotients of ADS, and so you can get at them with identifications. And so that there is an algorithm out there with a running time which probably isn't proved, but is based on that correspondence.
But you're saying that if you prepare the thermal field double state, you can trace out and get the other.
Yeah.
Can you say what are the next big challenges for complexity
Oh,
theory?
yes. Yeah. So I've been talking about the connection between wormhole length or wormhole volume and complexity, but this is an idea that has been generalized, that the wormhole volume is some integral over some region of space-time, and it's actually a kind of action, a natural kind of action called the Wheeler-DeWitt action of the bulk theory. And so the final version of the conjecture was that complexity was equal to action. And so I think one of the most interesting questions for a quantum algorithms or complexity crowd is still to try to prove that. And it's sort of been on my plate for a long time. It looks like a crazy, it looks like the rantings of a crazy person. Like, what's the most interesting thing in computer science? Complexity. What's the most natural quantity in physics? Action. They must be the same, right? But action is the phase accumulated in a time evolution. So it's naturally associated to the size of a circuit, right? And so this is not such a ridiculous thing to try to identify. And I have some feeling, some embryonic ideas about how this conjecture may have been originally made in the context of quantum gravity, but it may be something much more pedestrian about simulating semi-classical physics on a quantum computer. And so I would love to find some proof of this in a much more limited, controlled setting that just sort of explain why.
Well, I mean, can't one say, okay, plainly complexity is at most action, right? And the inequality will be tight unless there is a shortcut.
So yes, except that this action is not that action. So this is the action associated with preparing the state using a path interval. But I think the answer is, I still think the answer is more or less yes.
Okay.
But I would like to write that down carefully.
Okay. So maybe it's kind of like the situation with the time energy uncertainty principle in DeRita and Yossi Attia's paper, right? They're like physicists like assert something, and what they assert is sort of, more or less true, but it's true unless there is a computational shortcut.
Right. Yeah. And that's certainly going to be the case here. This would be, there exists an algorithm to simulate in which the dominant contribution to the running time is this action. Yeah.
Isn't this complexity here more like descriptive complexity than computational complexity?
Well, yes, but
Descriptive complexity, just say you just prepare the state and just do it for this amount of time, and so the descriptive complexity can always be tiny, right? Like if you mean like Kolmogorov complexity or whatever, that's always going to be tiny, right? I think you do mean computational complexity, like in terms of like number of gates.
But where's the computational problem, or I mean, don't know.
It's to prepare the space.
Okay, so quantum.
Well, actually, it's never been entirely clear to me. Is it to prepare the state, or is it to apply the unitary? Right? That's like, in many situations, those will be equivalent, right? But, you can say like they'll both increase linearly with time. But, you could imagine pulling those two apart.
Well, it's the complexity of the unitary. Well, I think it's this relative complexity. The number of gates required to convert the thermal field double state into.
Okay, right, but do we care about the entanglement with the other half? Like if we're tracking the entanglement, and we're only allowing a unitary on one half, then we could say that because of the Choi-Jamiakowski isomorphism, right, that like our complexity of our state preparation problem is just the complexity of applying a unitary, right? But if we don't care about the other half, then state complexity might be smaller. There might be a shortcut that's not available if we have to apply the whole unitary.
Okay, I have to think about that a little bit. I mean, the state is not maximally entangled. It has the thermal weights. And so if you try to use Choi-Jamiakowski to hop from one side to the other, it becomes non-unitary. Okay, but another question, what is the computational power of quantum gravity? And I know Umesh and some other people, and this is going to come up in Fermi's talk. Well, and also Bill and Umesh and Adam's paper suggested, or it suggests that a quantum theory of gravity might be able to compute things that are not possible in BQP. I think in their paper, in Adam et al.'s paper, the conclusion is that either quantum gravity can compute things that you can't compute in BQP, or the dictionary in ADS-CFT has to be exponentially complex. But it is an open question. How do you even formulate this notion of the computational power of quantum gravity? What is the task? Which observers do you talk about? What are the reasonable questions? And so a context in which that kind of question has been studied in an interesting way. If you set things up correctly in ADS-CFT, you imagine putting a computer in the bulk, and you send in multiple inputs from different parts of the boundary. You have the computer compute something, and then it sends portions of the output to different portions of the boundary. If you set up the geometry correctly, then what looks like a local computation in the bulk becomes an interesting distributed computation in the boundary. And it looks like ADS-CFT knows how to do those computations more efficiently than any protocols known to the quantum computing community. And so trying to, Alex May is the person who's really been pushing that line of thinking. But there are all kinds of questions about this. We don't even know that we can build a computer in ADS-CFT. We don't know that the theory is rich enough. So,
I mean, is there a hope of answering that question? Like, could one answer it by just showing that you can build a universal quantum computer within the CFT?
Yes, you could try to answer the question that way, but it's not so easy to build a universal computer in a CFT because the excitations are massless, right? And so, trying to build, imagine trying to.
Everything's too connected to everything else, kind of.
Yeah, it's hard to get structures that are going to sit there, right?
Yeah, right.
Yeah, so that students are thinking about those kinds of questions. There are questions that are relevant to more information theorists. But the entropies that are being calculated here are von Neumann entropies. But the various smooth one-shot entropies are of a lot of interest. We want to talk about these decoding questions. And it's not understood what the duals are of those one-shot entropies in the covariant formulation. And a big question, all of this is done, I said asymptotically flat space, ADS. It turns out things are much more confusing if you have an expanding universe. But that's where we live. So everything I've said, all bets are off in our universe, I should say. Right? We can't calculate anything at this point. So that's a smattering of the questions. There are many more. But yeah, I'd be happy to chat with people if they're interested, brainstorm good things to think about.
More questions.